Yeah, so we come to the magnetizing current in the real transformer. The magnetizing current, we call this IM, is a current proportional to the voltage applied to the core, and the lagging the applied voltage by 90 degrees. So if we still remember that we have, when we inject the current in the primary winding, it will create a flux and then transfer to the secondary winding. And how we describe the fluxes in the core is actually a graph. We can see here, this is the flux versus the mmf. Mmf means how the current that injected in the coil So it is actually changing from positive plane to negative plane. How is come like this here? Actually, we see here. So we have two graph here. Uh, this is one is a voltage applied versus a time, and then this is the flux linkage uh, that obtained in the maybe secondary or primary in the primary winding in the I'm not sure this one is it secondary, but I want to explain this one where when we apply the voltage okay, when we apply the voltage, actually the current, this is the current current versus time the current is lagging. uh, so for example, at this point when I apply peak voltage, maybe 10 volt, the flux in the core we can obtain is this one. At the same time, the magnetizing current will be at a peak as well. But there's a time delay, lagging by 90 degrees because of the inductive element. So second point, when this one, for example, 5 volt, we apply 5 volt, then I have my flux here. Then my magnetizing current will be going down as well. Same if a 0, 0, 0, negative 5, negative, so negative flux, negative uh, ampere, peak negative voltage, peak flux, then peak magnetizing currents. So this is how we interpret when we apply the voltage, the current is lagging by 90 degree. This is called lagging, lagging by 90 degree. So in this sentence, the magnetizing current IM for this graph is a current proportional to the voltage applied. It is proportional, you see. When it's peak, it is peak. When it's low, it is low. Proportional to the voltage applied, but it is lagging the applied voltage by 90 degree. So the current ratio, next we'll talk about the current ratio on the transformer and the dot convention. Same, we have a primary winding, we have a secondary winding, dot, dot, Vp, Ip, Vs, Is, Ip will go into the primary winding dot, Is will go out from the secondary winding dot. So we assume a load is connected to a secondary of a transformer. This is load. Dot convention. A current flowing into the dot end of a winding produces a positive magnetomotive force. So which means the current going inside this one, we will create a positive MMF. So IP is flowing into the dot, the MMF is FP. You still remember? F equals to phi R. Then F also equals to Ni. So now this is primary side. So Fp equals to Np/Ip. If Is is flowing out from the dot, the MMF is this one. So Is is flowing out from the dot. So my Fs equals to negative NSIS. And then net will be NPIP minus NSIS. How many NPIP injected? Well, how many NSIS will come out? So this is the net. So the net MMF must produce a net flux in the core, where F net equals to NPIP minus NSIS equals to phi R. So the flux flowing into the core. This is the net. Because the reluctance of the well-designed transformer core is very small, this is we assume the reluctance of the well-designed transformer core is very small until nearly zero. So the core is saturated. So which means when it's saturated, the N net will become a zero. Because R is very small, we can approximately zero. Then I'll move the other to the right hand side. NPIP equals to NSIS. Then I turn around. So it becomes IP IS equivalent to NS and P equals to 1A, 1 over A. This is why we call about the current ratio. Next, we will talk about practical transformer. Practical transformer has a hysteresis and eddy current losses. Then also we will talk about how to reduce the hysteresis losses, how to reduce the eddy current loss, reduce copper loss. Okay, in a practical transformer, this one is practical transformer. The losses in the core, it contains eddy current loss PE, hysteresis loss PH. So hysteresis loss, eddy current loss. Then losses in the coil. Coil is from the copper side. We call copper loss. But this is the three, majorly two component losses in the core, losses in the coil, but split into three, where which is eddy current loss, hysteresis loss, and copper loss. Wow. So let's go through. Hysteresis loss is energy losses due to hysteresis but don't write like this hysteresis is the dependence on the proceeding flux history and the resulting failure to retrace flux path. So this is called hysteresis. What is hysteresis phenomenon? Which is the dependence on the proceeding flux history and the resulting failure to retrace flux path. In easier way, the hysteresis loss is in the iron core is the energy required to accomplish the reorientation of domain. This is more to material science. During each cycle of the alternating current applied to the core. In short, it is area enclosed in the hysteresis loop. It can be shown that the area enclosed in the hysteresis loop formed by applying an alternating current AC to the core is directly proportional to the energy loss in an given AC cycle. How to minimize it? In order to reduce it, we reduce the amplitude of magnetic field within the material, or use magnetic material that have a narrow and a low hysteresis loop. For example, use soft core material. Okay. Just now we talked about dependence on the proceeding flux history and the resulting failure to retrace flux path, right? Hysteresis loss is the area inside this loop. So for example, now we need to know what is this. This is a pH curve, flux density versus magnetic field strength. How can we get magnetic field strength? When we apply current inside what we call the winding, that it will create a magnetic field, right? We call magnetic field strength, and then which means that this is proportional to the current. If you still remember, it is like this one. Okay. If I inject a current, okay, but the color not so nice, maybe I check. Blue. Okay. So if I inject a current, pen. I draw here. Okay. A coil. If I inject a current, then the field will create here. So this is the H, which is proportional to current, which means I can assume the current here. So if the current is positive going this side, so my flux density will at here, right? If I reduce my current, it will going down. If I increase in the negative way, which means I make the current like this, then the flux density will going to this way, right? Then I increase some more. From here to here, I increase some more. So the flux density will going to this side. Then I decrease my current. Then it will go back. Then I increase again my current. It will go to this path. And then I increase again my current. It will go to this way. So we can see that from this point to this point, then go back to this point, then go back again to here. For this current, okay, it is actually an AC, right now. So which means if this is an AC, okay, and then this is the core, we have a core inside. So the core will experience the go up, the core will experience this one. Core will experience going up, then reduce, then going down, reduce, then increase the magnitude, then decrease again, then decrease again, then increase. This area, we call this area it is a hysteresis loss. Okay, so the hysteresis loss is actually the area enclosed in the hysteresis loop. So the process from here going up, down, this is the hysteresis loop. Okay, so eddy current loss, the current energy loss due to the eddy current. Eddy current, what is that? Actually, it's a current. Okay, the current induced in the iron core by a changing magnetic flux produces energy loss in the material. How to minimize it? We use a lamination of the material. Then the maximum size of a current, swell means circulate, will be reduced. The resultant in the lower induced voltage, a lower current, and lower losses. How to minimize it? We will increase the resistivity of the core material. First of all, we need. Oh, just now I did not finish explain this one. So BH, maybe do I have this one? Okay, eddy current. Let's go to eddy current first. So eddy current losses within a transformer core cannot be eliminated completely lah. So for example, this core, there's no laminated, means this is one solid core. It become like this. When we insert AC here, okay, it will create eddy current like this. Swell means circulate lah. Okay, so they can be greatly reduced and controlled by reducing the thickness of the steel core through lamination. Reducing the thickness, and then resistance will be increased and the current will be greatly reduced. V equals to IR. Okay, when R increase, I will be decreased. I can say like this but this is not constant. And then okay, in order to minimize this one, we need to segmentize it. Okay, we need to segmentize it, become this one. We call this one as a laminated core. And then the smaller the area, okay, the smaller the higher the resistance. Actually, they according to this formula, R equals to rho L divided by A. So if my area decrease, my resistance will increase. Yes. Okay, my area decrease, my resistance will increase. When my resistance increase, it will decrease the current. It will stop the current, saying, hey, my resistance is high, don't come to play around with me. Okay, that's why this is how we reduce the eddy current. First of all, we need to understand how the eddy current produced. Eddy current only produced when there's a AC. Okay, if we inject DC here, no eddy current. No eddy current. So this is what we talk about the eddy current loss lah. The current induced in the iron core by changing magnetic field. In order how to find the changing magnetic field, we put the AC current. Okay, how to reduce it? We laminate it, or we use a higher resistivity of the core material. Okay, for the BH curve, we have a broad curve. We also have a narrow curve. So broad curve, the hysteresis loss will be higher lah. Narrow curve, the hysteresis loss will be lower. At the same time, hysteresis loss also happen in the AC field. You see, from H proportional to I, from 0 increase to positive, maybe positive 10 ampere. Then from 10 ampere decrease to 0, and then I increase again to negative 10, so negative plane. Then I decrease again to 0, then I increase again back to 10. So it is, in fact, it is a AC. Okay. So yeah, for example, if let's say my mu is infinity, actually my hysteresis will be 0. Then mu infinity, saturation will also infinity. Okay. Then once it is infinity, my current will be 0 and hysteresis will be 0. Okay. This one pH curve, the slope will give us the mu value. Or if we still remember, B equals to mu H. Okay. So how to find my mu? Actually, mu equals to B divided by H, which is the slope, this one. So B is this one. Okay. H is this one. Right? So I use B divided by H. This is my mu. So mu infinity, it is a straight line like this. And then my hysteresis will be 0. So next, how to reduce the copper loss? Transformer copper loss are mainly due to the electrical resistance of the primary and secondary windings. Conductors of a large diameters are used in order to reduce the resistance per unit length. R equals to rho L over A. So large diameter will be higher resistance. When R increase, when A increase, R will decrease. So improve the winding technique. One of it is we reduce the resistance per unit length. One of it is we improve the winding techniques. Another one, we use a material with higher electrical conductivities or lower resistivity, such as copper. Just a comparison. What we have a talk about is the ideal transformer and also the practical transformer. So ideal transformer, let's go through, compare one by one. Ideal transformer, the mu will be go to the infinity. Practical transformer, mu will be finite value. It has some value. And then ideal transformer, we have when mu is infinity, saturation will be 0. And then for practical transformer, the saturation will be some value. And then ideal transformer, no hysteresis loop. Finite area will have a hysteresis loop. And then ideal transformer, the resistivity will become infinity, eddy current will become 0, coil resistance will be 0, coil resistance will be 0. And then practical one, we have a resistivity in a core material, we have a coil winding resistance in a winding. Okay, so